This episode of Ask Mr. G is once again based on a question asked during a stream of the week where somebody wanted to know. And during the stream, I was kind of like, well, obviously, the sun doesn't have a shadow. And a bunch of people in chat were like, the sun doesn't have a shadow. The sun radiates light in all directions. How can it cast a shadow if it of itself gives off light? Well, thought about it again. You have to look at the current field of mass spectrometry, in which we take some sample, usually a gas, once it passes through the ionized chamber, and in of itself becomes ionized due to extra energy by electrons, then it passes through a series of magnetic fields. And when it passes through those magnetic fields, the sample then separates based on mass and reaches a detector. So a very complicated machine that takes a sample, ionizes it into a vapor, or ionizes a vapor, a gas, the resulting material, having it land on a detector based on its mass, and then using some kind of computer or analysis tool to translate this into a graph where you have certain material transmitting a certain wavelength and having a certain energy. And so you can determine the elements and compounds that make up your sample, and it becomes almost a barcode of what your material is made out of. So some unknown sample can have an identity based on ionizing the material, separating based on mass, and looking at the energy in which it took in the electrons to give off the electrons, and that resulting spike in energy. So this energy and ionization is based on radiation, and we know light as radiation, specifically electromagnetic radiation. What we're familiar with is the visible spectrum that we set as the center of this electromagnetic spectrum. However, there's other types of radiation. You go a little bit beyond Roy G. Biv, and you have ultraviolet. Then you have light that can penetrate more matter, more material. You can have X-rays. And then the most energetic, the shortest wavelength type of light we have are gamma rays. Short wavelength, highest energy. On the other side of the spectrum, below red is infrared, and then below that, microwaves, and then really long wavelength but low energy, we have radio waves. So there's all types of light. You only see a tiny slice of the whole electromagnetic spectrum. How we knew light has different types is because of Sir Isaac Newton taking a glass prism and having light into the series of colors we know as the rainbow, where violet being shortest wavelength, highest energy, and red being the longest wavelength and the lowest energy. Take this PhET simulator as an example. We turn on our flashlight, we'll take a prism and place it in front of the flashlight, and we can turn the prism to have it refract the light into the spectrum, and other prisms to get a wider range of that rainbow effect. And so before becoming a teacher, my focus was on biology and studying a little bit of chemistry, especially organic chemistry. And this is one of our labs that we did using NMR spectroscopy, similar to spectrometry in that we are using nuclear magnetic resonance to separate material based on their chemical and their physical properties. And taking that unknown sample, looking at the signatures of carbon and hydrogen and oxygen. This sample had oxygen in it based on the data that we got back from the machine. So again, using wavelength of light, but coming from compounds, we can use that light and the wavelength to determine what compounds they are, because each compound has a very specific wavelength of light that it can emit based on energy given. Another lab used infrared light added to a substance, so basically pumping a lot of heat into the substance, and the result, looking at the different chemical orientations of these compounds and molecules and elements within those compounds to determine what this substance was. This is the actual graph that came back. Being able to use these spikes in loss of energy because the molecules have absorbed it, we can look at the loss of energy, at what frequency and at what wavelength that was done at. You can then determine what each of these compounds are. So, does the sun have a shadow? Joseph Fraunhofer, in 1815, decided, I'm going to take sunlight, and like Sir Isaac Newton did with put it in a prism, I'm going to take sunlight and I'm going to put it into a prism to refract the sun's actual light, but then analyze it in greater detail. And so he took the light from the sun, given off at the photosphere. And what he found out is there was not a complete spectrum of violet to red. Instead, there were black lines inside the spectrum. And these black lines meant that some of the light from the sun was being absorbed. What was absorbing it? Cooler gas outside at the edge of the corona, the sun's atmosphere, was absorbing the light coming from the photosphere, the surface of the sun. And these gases were absorbing certain wavelengths of light. These wavelengths did not reach Fraunhofer back on Earth, so what resulted in a series of black lines inside the spectrum. And so the sun, while it didn't really have a major shadow, there's a shadow inside its spectrum, and it acts as a fingerprint. And you can use this to determine what elements and compounds are near or at the sun, like oxygen gas, and sodium, and hydrogen, and helium, and the simple compounds based off of those are near the sun, and you can use it to determine the makeup of the sun. Well, this stellar spectra has been applied to other stars, and into the 20th century, the field of astronomy, and what we've determined is, again, looking at wavelength versus energy, in this case, brightness from a star, we've developed this idea that all objects in the universe produce a spectrum of black body radiation. A black body would be something that gives off no light, and therefore gives off none of this curvature inside a bright versus wavelength graph. And different stars have different amounts of brightness versus wavelength and different absences in their spectra. And this can be used to analyze and classify. So our star being a yellow dwarf compared to Betelgeuse in the constellation Orion being a red supergiant. This allowed astronomy as a scientific field to boom in the 20th century, and all kinds of scientists classifying and analyzing stars according to their spectra, which led to Edwin Hubble eventually observing stars, other galaxies, and then their properties of those galaxies. He saw the light of other galaxies starting to redshift, which means their light was being stretched, because purple light will be stretched to indigo, and indigo gets stretched to blue, and blue gets stretched to green, so on and so forth. So all light will eventually become red shifted, in that the wavelength becomes larger and becomes more red-like. So if galaxies are red-shifting, these other galaxies are moving away from us. And so Edwin Hubble in the 20th century, based on looking at this light coming from stars and other galaxies, determined that our universe is actually expanding. So now today, the point of the sun's shadow, what can we use this next leap in astronomy? NASA's going to launch the James Webb Telescope sometime soon. The date's been changing back and forth based on budgeting and other financial issue, but we're hoping that it finally is launched in 2021, about a year from now, March, February. And this telescope's going to be in orbit around the Earth, and it's going to look at other stars, and especially stars with exoplanets, planets not part of our solar system. And the James Webb Telescope is going to wait for this planet to move in front of its star, almost like an eclipse, but it's called a transit, and it's going to allow some of that starlight to go through that planet's atmosphere. And just like Joseph Fraunhofer looking at the spectra of our star, our sun, and analyzing its signature, the James Webb Telescope and the astronomers working at NASA and around the planet are going to look at the spectra of exoplanets. And this spectra from the exoplanet will allow us to look for, once again, those compounds and molecules that have certain signatures in energy when received from an outside source. So think of this as a really large nature-based mass spectrometer that will look for organic compounds on exoplanets. And if there's organic compounds on exoplanets, maybe there's a chance for life. All because, yes, the sun has a shadow.